Okay, we're going to make sure we skip the rational root theorem. This is section 6.5, but don't worry about that rational root theorem if you see that in the book. Also, when you get to any questions that talk about the rational root theorem in the book, you can ignore those instructions. In order to factor a polynomial of degree 3 or higher, we need to have a clue or a hint. So don't think that you won't have to have a clue or a hint. I'll make sure that you have one on the homework questions as well as the quiz and the tests. Okay, so our first example that doesn't deal with the rational root theorem is example 2, and it says find the roots of, and I made up a different problem than the one that's in the book, x cubed minus 2x squared plus 5x minus 10 equals 0. Now the only way to solve this or find the solutions to this is to know one of them. So you start out knowing that 2 is a solution. So in order to find out the other solutions, I have to divide this by that value 2. In other words, we're talking about saying that x minus 2 is a factor, which also is the same thing as saying that 2 is a solution. So doing my synthetic division, I carry down my 1. I multiply these two together and write that number down here. And then I add the numbers in that column. And I'm going to multiply again and add. And I'm going to multiply again and add. So we end up with, we started with a cubic, we took out a linear factor, so this is a quadratic term. The linear term does not exist because it's a 0. We have a constant term of 5. Alright, so this is what we've reduced this to. Our original equation has now been reduced to the original x minus 2 and x squared plus 5. Okay, that's what we just divided that original thing down into. The hint that they gave me plus what I found when I divided. Now, setting each of the factors equal to 0, well, I already know what I get from the first one. I get the number 2. Okay, so don't think that we don't have to write that down as one of our solutions. But now I need to find what the others are. So, this one doesn't have a linear factor, so I don't have to use the quadratic formula. So I can subtract the 5 to the other side. I can take the square root. When I take the square root in a solving situation, don't forget your plus and minus. Keep in mind that what you really have here is the square root of negative 1 and the square root of 5. Now, do you know any perfect squares which go into 5? Neither do I. So we can't simplify the 5 at all. But I can simplify this, right? Because we remember that the square root of negative 1 is I. And then I've got my leftover radical 5. So we want to simplify those radicals as much as we can. So, for instance, let's just suppose I was doing a different problem and totally separate issue. I came out with x squared equals negative 8. Okay? Make sure when you come up with those situations, you take the square root of both sides, that you get x equals, you got square root negative 4 and square root 2, right? You pull your perfect square out with the negative 1, leaving everything else inside. So that would be plus and minus 2i radical 2. So if you, I know this problem has nothing to do with the 5 and over here, nothing to do with it at all. Okay, I just wanted to show you a quick example of something that you would need to simplify by pulling out perfect squares if you had to do that. This example, however, didn't. So we have 3 solutions. The original one that I gave you, 2, and then we found 2 more, plus and minus I radical 5. Oh, look! A conjugate pair. Oops, can't spell. Now, why am I making a big deal out of that? Conjugates. We have seen them before, okay? So let me just refresh your memory. Polynomial conjugates look like this. X minus 2, x plus 2. We saw those when we factored the difference of squares. Irrational conjugates, here we got 2 plus radical 5 and 2 minus radical 5. That's what irrational conjugates look like. Imaginary or complex conjugates look like this. Negative 3 minus 7i, negative 3 plus 7i. So take a look at what you see there. The first term is staying the same. It's the second one that's changing sign. First one stays the same. Second one changes sign. Okay, there's a couple of theorems that you need to know. The irrational root theorem. The irrational root theorem says irrational solutions come in conjugate pairs. That's an important theorem. It says that every time you have one irrational solution, you know that its conjugate brother goes with it. So if you know 7 minus radical 5 is a solution, then 7 plus radical 5 is also a solution. They come in conjugate pairs. If you know one, you automatically know the other. Guess what? What do you think the imaginary root theorem says? The imaginary root theorem says that imaginary solutions come in conjugate pairs. If 4 plus 2i is a solution, then so is 4 minus 2i. It's just as simple as that. Now the last example that you need is from example 5. In example 5 it says find a third degree polynomial in standard form with roots of 3 and 1 plus I. Well, if you know 3, what is the factor that comes from that? Yes, it's x minus 3. If you know 1 plus I, what other solution do you also know? Yes, you know its conjugate, 1 minus I. Now, how do you write the factors from those? Those are kind of unusual. Well, keep in mind, every factor in the universe is written x minus a number. I know you don't believe me because you're like, well, what about the x plus 2 or the x plus 7? Well, keep in mind, if negative 5 is a solution, then what is x minus negative 5? Oh yeah, that's x plus 5. Right, that's why you get x plus 5. But in all reality, every factor in the universe is written x minus. So this one would be written x minus 1 plus I. This factor would be written x minus 1 minus I. Now, a third degree polynomial has 3 solutions. Do we have them all? Sure we do, right here. 1, 2, 3. Now, it says that the problem says we want it in standard form. I'm starting with factored form. And I'm going to change it to the standard form. Sorry, move it around. Okay, so I'm going to do a little bit of distributing here, just a tiny bit. X minus 1 minus I, x minus 1 plus I. Now, I know that some of you are into FOIL and what I call the bombing technique because you're drawing arrows all over the place, but I'm not. I like to box. I know the foilers are screaming right now. No, don't do that to me. Well, sorry. I've got to organize my information. I don't like losing it. So I'm going to use these up here to be the headings of the columns. And I'm taking this one and I'm writing it down the side to be the headings of the rows. And then I'm going to match the boxes up. So I've got x squared minus x, xi, minus x, plus 1, minus I, negative xi, positive I, and minus I squared. Everybody and their brother should know that minus I squared is really positive 1, right? Because we know that I squared equals negative 1, therefore minus I squared would be positive 1. Well, look here. Those two are opposites, they cancel out. These two are opposites, they cancel out. So these two are like terms. These two are like terms. That gives me x squared minus 2x plus 2. Now don't forget about the x minus 3 that we had sitting out there. Oops. Sorry, I'm all messed up. Well, I'm just going to continue to make a bigger box. That's all I'm going to do. Or another box, I should say, not necessarily bigger. Okay. And then I'm going to match things up. X times x squared is x cubed minus 2x squared plus 2x minus 3x squared 6x and minus 6. Add my like terms together. These two are like terms and these two are like terms. So I have x cubed minus 5x squared plus 8x minus 6. Now, I didn't put equals y next to it because it did not say a polynomial function. It just said a polynomial. That's why I left it the way it is. You don't see me writing equals y. Now, if it says polynomial function, you better believe I expect you to put equals y on there.